Hi, everybody. We're back for the final portion of Unit 4, Chapter 4, dealing with probability. And we're starting in Section 4 of Chapter 4, dealing with counting principles. So, counting is really where a lot of probability is based on, knowing how many possible values there are and compared to how many meet the requirements we're looking at is the basis of classical or theoretical probability. There are a lot of formulas in this chapter, in this section, so be prepared to write them down and record them. This is one section where the whole common sense approach just doesn't really work. So we're going to start off with the multiplication rule. Now, the multiplication rule is simply saying if I have different things that I need to select and I have a number of choices for each of them, I multiply that number of choices together to get the total number of options. For example, let's look at a meal. Let's say you have 2 main dishes, 3 vegetables, 2 desserts, and 4 drinks to choose from. Your options for meals would be 2 times 3 times 2 times 4, giving you 48 different meals that you could choose from. That is the basis of the multiplication rule. So the example the textbook uses is trying to guess a computer password where we use all the characters on the keyboard. Standard keyboard has 92 options. That's your letters, both capital and small, your numbers, your symbols, and all that. If we have a 5-letter or 5-character password, the number of possible passwords is 92 for the first, 92 for possible characters for the first element, 92 for the second, 92 for the third, and the fourth and the fifth. Multiply those together, we get 6,590,815,232 possible passwords. That's a lot. Getting this correct on the first attempt is almost impossible. Getting it correct on the first thousands attempts is still less than 1 in a million. So to speed up this counting, we're going to look at some rules here. The factorial rule comes into place when once you've selected something, there's no replacement. It doesn't go back in. So factorial is symbolized with a exclamation point. And what it's saying is you take that number and you multiply it by every integer going smaller until you hit down to 1. So 5 factorial would be 5 times 4 times 3 times 2 times 1, which multiplies up to be 120. Special definition, 0 factorial is defined to be 1. It comes up enough that it works. It's based on the principle that if I'm selecting, let's say I have 5 students and I'm going to put them in line, and I'm just randomly selecting students. Well, there are 5 different students I could select for the first place in line, 4 for the next place, 3 for the next place because I've already got 2 of them already in line, only 2 more left to choose for the fourth place. In the last place, there's only 1 student left, so that student has to go in that place. So getting all those possibilities, we just multiply those together. So the factorial rule is very handy in counting. Let's look at scrambling letters. So we want to look at the word steam, 5 letters. First question we want to ask is how can it be rearranged? How many different ways can we rearrange those letters? Not worrying about if they make a word or not. Also then, what's the probability that they get arranged in alphabetical order? Well, there's only 1 alphabetical order for the letters in steam. And then how many different words can be formed by those letters? So first of all, how many different ways to rearrange them is just 5 factorial or 120. There are 5 letters. Again, there's 5 ways I could randomly select the first letter. There's only 4 more letters left for the second, 3 for the third, on down. That's 5 factorial. So there are 120 ways that we could rearrange those letters just randomly, not worrying about what order they're in. Alphabetical order would be A-E-M-S-T. There's only one way to do that, so the probability that they randomly get arranged into alphabetical order is 1 out of 120, because there was 120 possible ways to rearrange them. Only one of those gives us alphabetical order. The factorial doesn't help us calculate how many different words we can form with those letters. We have to just scramble and unscramble them to see how many different words we can make. We got teams, meets, mates, and tames are the words we were able to find. There's 4 of them, plus steam itself, for a total of 5 words that we can form with those letters. The chances of forming a word if you randomly rearrange the letters is 5 out of 120, but that's not what we were asking. We were asking how many words you can make. Our statistical counting techniques don't help us here because we had to arrange the letters into words, and we did that brute force. So a permutations and combinations both utilize the factorial notation to do counting. There is some very important differences between permutations and combinations. Permutations are rearranging things. Now, the factorial was using them all up. The permutation is only using a certain number. We don't have to use all of them up. The key in a permutation is the order matters. So if I am rearranging the letters ABC, well, ABC is different from ACB, which is different from BAC. They're the same 3 letters, but they're in different orders. Those would all be counted as different arrangements for a permutation. So we're looking at different sequences. We're looking at letters, what order the letters are in and what letter follows others. When we're dealing with a permutation, that's why that matters. The order does matter. Otherwise, once we get to combinations, those 3 letters, as long as they're the same 3 letters, it doesn't matter what the order they're in. Those are all considered to be the same combination. So that would be considered one combination, even though there's 6 different permutations for those 3 letters. So let's calculate. Permutations, position. Combinations, committee. So the example they use is, let's say we have a club, and our club has a certain number of members in it. Let's say we have 10 members in our club. And we want to select officers, president, secretary, and treasurer. Well, there's 3 different places to select there. It matters whether you're chosen for president or secretary. It makes a difference. That is a permutation because the order matters, different positions. If I just want to select a committee, I'm going to do roadside cleanup. So a 3-person committee. Nobody's in charge. All of them are going to do the exact same tasks. So there it doesn't matter. Order does not matter. If you're selected first or if you're selected third, you're on the same committee. You have the same responsibilities. So our calculation for a permutation, where N is the number of items available to be used, and R is the number that we're going to use, again, without replacement. If we put them back, if we replace them, that's different. The N thing, so we pronounce it N things permutated R at a time, NPR. It's N factorial over N minus R factorial. So our example here, selecting the trifecta. So for horses, we have 20 horses running in the race. We want the first place, second place, and third place. It does matter. We're not just picking the top 3 horses. We're picking them in order. This is a permutation. So of those 20 horses, we want to know how many different trifecta bets are possible. And then if we randomly select them, what's the probability of actually getting the trifecta? So there's 20 horses available, so N equals 20. We are selecting 3 of them, first, second, and third, so R equals 3. So it's 20 permutate 3 at a time is 20 factorial over 20 minus 3, which is 17 factorial. That ends up being just 20 times 19 times 18 if you calculate it out, giving us 6,840 different possible finishing positions. Now, this, of course, is assuming that each horse is equally likely to win, equally likely to place. There are some horses, of course, that are out there just to fill spots. They have no chance of being in the top 3, but we leave that possibility out there when we do these calculations. So there are 6,840 different possible arrangements of those 3 horses in the top 3 spots. So that means the chances of randomly selecting the trifecta are 1 out of 6,840. If there are 6,840 different possible bets, not all of them have the same chance of winning because certain horses, as I said, are more likely to place in the top 3. Some have no chance. So because of that, the chances are a little bit better than 1 out of 6,840. This is why it doesn't pay $6,000 for every dollar you bet. So for the permutation rule, if we have repeated items, so the one we've done so far is when all of them are separate, all of them are different. But what if we have some items that are the same as each other? Well, now we have certain combinations that would be just the same. If we have multiple A's and they're AAB or AAB, if the A is switched, it's still the same set of numbers. So to account for that, do that counting, we divide by, so we start out with the total number of items available, factorial. And then if we have several that are the same, we have that number factorial divided by the next set that's the same, and so on. And we'll demonstrate that here in this example. So for surveys, a lot of times in a survey, they'll ask identical questions just to ensure that the person being surveyed gives the same answer. It's to stop people from just throwing out random answers to get through the survey quickly to get a reward. And so in this survey, they've got one set of 2 questions that are the same, slightly superficial differences in wording so that you don't immediately recognize them as the same question, and another set of 3 questions that are the same question. So how many different arrangements of this survey are there? So there's 10 questions in the whole survey. That's N. 2 of them are the same. That's going to be N1. And 3 that are the same, that'll be N2. So the formula will become 10 factorial, which is the 3,628,800, divided by 2 factorial, which is just 2 times 1 or 2, and 3 factorial, 3 times 2 times 1 is 6. So, of course, that's 12. The 3,628,800 divided by 12 gives us 302,400. So even with those repeated questions, there's still 302,400 different random arrangements of the questions in that survey. So the question is it possible to survey enough people so that all the different combinations or arrangements, I should say, of questions are set, all the different permutations of questions are used? Not unless we're going to survey 300,000 people. Typically, we only survey about 1,000. So next is a combination. A combination is still done without replacement, but remember the order doesn't matter. Whether you're selected first or last, you're going to be in the same group. So the formula here is slightly different. N is the number of items available again. R is the number we're choosing. So it's N factorial over N minus R factorial. That's the same as the permutation, but then we also divide by an additional R factorial. That's to account for the different orders of each set of numbers, set of items. So here we're going to look at the Florida's Cash 5 lottery games. You choose 5 different numbers from 1 to 35. How many different lottery tickets are possible? and find the probability of winning a jackpot with only one ticket purchased. So it's 35 numbers, and we're going to choose 5 of them, no replacement. So n is 35, r is 5, so 35 minus 5 will be 30 factorial, and 5 factorial. Calculating that out, there's 324,632 different possible lottery tickets that could be sold. Which means the chances of randomly selecting the winning numbers are 1 out of 324,632. They crack a little bit of a joke here talking about this is why lottery is considered a tax on people who are poor at math, because playing the lottery to get rich is very, very highly unlikely to happen. The chances of winning are very, very small. Okay, so moving on then to the last section of chapter 4. And we're going to breeze through this pretty quickly. This is about using simulation to estimate probabilities and to estimate whether we have statistical significance or not, basically for hypothesis testing. And so what we're looking to do is we're looking to see if the chances of something happening are either significantly small, highly unlikely, or significantly large, extremely likely, but if it doesn't happen, then something went wrong. So a simulation is just any sort of a procedure where we simulate a real process, hopefully getting results that are similar. Now, in reality, simulations are, in many cases, are not totally practical because we'd have to know the probabilities in order to accurately set up the whole simulation to make it work. So simulations only work in special cases where there are things that we can account for without having to know the answer to the problem. So 2 good uses. We can test a claim. So part of the whole hypothesis testing thing we're going to get into in a couple of weeks is we make an assumption, and then we gather data and we compare that data to the assumption. Well, if our data results are very unlikely given the assumption, then we have to go back and assume that the assumption was incorrect. Next is we can use a simulation to estimate a probability of a complex event. For a simple event, we have to know the probability before we could estimate it, so it doesn't make much sense there. But a complex event that requires multiple things to happen at the same time, that's where a simulation is useful for calculating probabilities. So one example that gets used a lot is testing the claim if mean body temperature of human beings is 98.6 degrees Fahrenheit. So we start out by assuming that that is true, that the mean body temperature is 98.6 degrees Fahrenheit. Then we're going to gather data and compare the results of the data to that claim. So we select 106 people. We find their body temperature and find that the mean body temperature of those 106 people is 98.2 degrees Fahrenheit with a standard deviation of 0.62. Now, we don't know anything about sampling distributions and how we combine all that to tell whether this is highly unlikely or not. But if this result of taking a sample of 106 people and getting a mean of 98.2 degrees, if getting that result is highly unlikely based on the assumption that the mean temperature really is 98.6, if this is highly unlikely, then we would have to assume or conclude that that assumption was wrong. So that's basically what they're going over here, is if we conclude that getting that sample result of 98.2 is very unlikely, assuming that our basic assumption of 98.6 degrees being the mean temperature, then we go back and have to assume that assumption was not correct, because the probability of getting 98.2 as our mean in our sample is significantly low, usually less than 5% or less than 0.05. So it appears, again, we didn't do the sampling distribution stuff. That'll come in a couple of weeks. But at this point, we're going to say that it is very unlikely, given the assumption that the mean really is 98.6. So we assume the assumption was incorrect. So there's our summary of the results right there. We could use a simulation to do this. Here, though, we can't set up a computer to randomly generate these things, because for the computer to randomly generate body temperatures, we would have to input the mean and standard deviation. Well, we don't know those. That's what we're testing. But here our simulation is selecting people and measuring their temperature. Well, the next thing that we can try to estimate is a complex probability. We want to look at a population, and we want to, well, this is actually just summarizing still that making a conclusion about a population mean. We assumed we knew the population mean. We gathered data that was significantly different than that. So we assumed that we were wrong. Next, though, we want to look at, well, what is calculating a probability of an event occurring? And the event that we're going to look at here is, if we randomly select 100 people, what is the probability that at least 3 of them will have the same birthday? So to do this, we number our days of the year 1 through 365, assuming this is not a leap year. And then so we select people's birthdays. So what we're going to do is we're going to take a database of people and their birthdays, and we're going to use the computer to randomly select 100 of those birthdays. Or we know that birthdays are evenly distributed throughout the days of the year. There's no day of the year that's more likely to have birthdays than others. Not totally true. Power outages and stuff like that skew that probability a little bit. But for the most part, there's pretty close to an equal number of births on every day of the year. So here we could use a computer simulation to just randomly select numbers between 1 and 365 to simulate people's birthdays. So we do that. We set up a computer simulation to randomly select 100 numbers to generate 100 numbers between 1 and 365. And then we sort them from smallest to largest. Then we look through the list here. We see that we got 3 that are at 113 and 3 that are 192. So we not only got 3 birthdays on the same day, we had 2 sets of 3 birthdays on the same day. And then for our simulate, this was one run or one trial of the simulation. For the simulation to work, we would have to repeat this with several trials over and over again and count, check to see, did we get 3 or more birthdays that are the same in this set of 100? Yeah, if it's yes, we put that in the success column. If it's no, we put it in the failure column. And when we're all done, we can use that to calculate an estimated probability. So for the most part, what we're going to be doing in this course, we're not going to be doing the probability estimates of simulations. We're going to be doing the hypothesis testing here, where we make an assumption. That's the basis of hypothesis testing. And then we gather data and compare the results of our data to that assumption to see if the result we got was highly unlikely. So there's a lot in this chapter. Probability, as I've mentioned before, is where people struggle because it's a different way of thinking. Most of us have had the basic statistics before, but probability is where we start to get into stuff that is new to this course and that many have not seen before. So please make sure you're taking your time through here and asking questions as needed.